Everyone says electricity flows through wires like water, through pipes. You flip the switch, current flows, the bulb lights up. Simple, right? But what actually moves when you flip that switch? Electrons, sure, but how fast do they move? A few inches per hour. That's not a metaphor. That's the actual drift velocity of electrons through copper wire. So then, how does your light turn on instantly when you flip the switch 100 feet away? What's really happening in that wire? Current flows is just describing what you see, not what's actually there. The truth is stranger. Electricity isn't a thing moving through wires at all. The reason has nothing to do with particles traveling. It's about what a field is. The common picture everyone carries around is electrons as little balls rushing through the wire like water molecules through a pipe. Your teacher probably drew it that way, arrows showing the direction of flow, maybe even little circles with minus signs on them marching along. It seems to make perfect sense. Something must be traveling fast to deliver energy that quickly, right? But measure it. Actually measure the drift velocity of electrons in a current-carrying wire. Glacial. Inches per hour through copper. And yet electromagnetic signals, the actual propagation of electrical effects, travel at nearly the speed of light through the wire. Light speed. You flip a switch on one end of a 100-foot cable, the bulb at the other end responds essentially instantaneously. If the electrons had to physically travel that distance at inches per hour, you'd be waiting all day for your lights to come on. You're not waiting. The effect is immediate. So what actually moved? Not the electrons. They're still crawling along at their glacial pace, bumping into atoms, drifting slowly through the conductor. Something else is propagating at light speed. What is it? The field. The electromagnetic field. That's what moves. Not particles, the field itself. And here's what you need to understand. That field was already there before you flipped the switch. It already filled the space around and in the wire. It's not created by the electrons and it doesn't travel with them. It's already present, permeating the space. When you close the circuit, you change the configuration of that field, and that change, that disturbance in the field, propagates outward at light speed. But what is a field? Most people, even people who've taken physics, think a field is just a mathematical description, a convenient way to calculate forces at a distance. Numbers on a grid, a computational tool. No, the field is the fundamental thing. It's real, it has physical properties, it carries energy, momentum. Space itself has structure, tension, properties that we describe with the electromagnetic field. You can think of it like a rubber sheet with objects creating dips and curves, except that's gravity. The electromagnetic field doesn't need any medium at all. It's not in space. It is a property of space itself. When you wiggle a charge, you disturb this field. That disturbance propagates outward like, well, not exactly like a wave in water, because water is a medium and the electromagnetic field isn't in anything. More like a ripple in the tension of space itself. The field carries energy from one place to another. Real, measurable energy. The wire doesn't carry electricity. The field around it does. Think about what that means for the wire. What's the wire's job? To create the field pattern. Moving charges in the wire, those slowly drifting electrons, produce a changing magnetic field around the wire. A changing magnetic field produces a changing electric field. These changes propagate outward through space at the speed of light. The wire constrains the geometry of the field, keeps it organized in a useful pattern. But the energy, the actual energy, flows in the space around the wire, not inside it. There's a quantity called the Poynting vector that describes energy flux in electromagnetic fields. It points perpendicular to the wire surface. The energy flows in the field surrounding the conductor, not through the conductor itself. We can measure this. Energy density in the field versus in the wire material, the field wins by an enormous margin. The telegraph operators in the 1850s knew something was strange. When they laid the transatlantic cable, they noticed that signals propagated far faster than any particle could possibly move through thousands of miles of copper wire. They called it retardation and blamed it on the ocean affecting the cable. Wrong reason, right observation. The signals were traveling as electromagnetic field disturbances, not as particle motion. They couldn't have known that. Field theory didn't exist yet in any complete form, but they stumbled on the evidence, which means the electrons barely matter at all. They're just there to guide the field, to create the pattern. So you might ask, if the field carries the energy, why do we need wires at all? Why not just skip the wire? And the answer is, you can. Radio does exactly that. Broadcast transmission, no wires. But here's the thing, the wire's advantage is confinement. It keeps the field organized in a useful pattern, concentrated along the path you want. Without the wire, the field spreads out in all directions, radiating away, weakening with distance. The wire prevents energy from dispersing into space. Think of the electrons in the wire like shepherds guiding a flock. They keep the electromagnetic field corralled, moving where you want it to go. The wire is a fence for the electromagnetic field, not a pipe for electron fluid. Without that fence, your field spreads out and most of the energy never reaches its destination. With the wire, the field stays coherent, concentrated, guided. But here's what should blow your mind about alternating current. In direct current, electrons drift in one direction, slowly as we've established, but they do have a net displacement over time. In alternating current, the electrons don't go anywhere at all. They oscillate back and forth. In America, at 60 Hz, the electrons reverse direction 120 times per second. The average displacement is 0. The electrons in your wall socket never leave the wire. They vibrate in place, forward and back, endlessly. Yet energy pours into your house continuously, powering everything. How? Field oscillation. The electrons wiggle. That creates an oscillating magnetic field. The oscillating magnetic field creates an oscillating electric field. And that oscillation, that wave in the field, propagates outward, carrying energy. The field does all the work. Edison insisted that direct current was real electricity precisely because something actually moved a net distance. He thought AC was somehow fake or inferior because the charge carriers didn't have net displacement. He was completely wrong about what mattered. The field oscillation carries power perfectly well. Better actually, because AC can transform voltages easily. That's what a transformer does. You've got one coil carrying AC current. That creates an oscillating magnetic field. That field passes through a second coil nearby. No physical connection between the coils, just the shared field. The oscillating magnetic field induces a voltage in the secondary coil. Field coupling, not particle transfer. Different numbers of turns in the coils give you different voltage ratios. That's why we can transmit power at high voltage, loses less energy to resistance in long transmission lines, and then step it down to safe levels for your house. Every device in your home runs on electrons that never went anywhere. They just jiggled. The energy came through the field. So current flows is wrong twice. Wrong about what flows. It's not particles, it's field disturbance. And wrong about flowing at all. In AC, nothing flows. The field oscillates, and that oscillation carries energy. You start to see why I found this so compelling. The whole conventional picture is backwards. People thought electricity was about moving charges. It's not. It's about field dynamics. The charges are secondary. They manipulate the field. Every physical system has a natural frequency at which it wants to oscillate. A swing, a wine glass, a radio antenna. My great insight, though I didn't discover the principle, I just saw how to use it, was that electromagnetic systems resonate just like mechanical ones. When the driving frequency matches the natural frequency, the amplitude explodes. Push a child on a swing at exactly the right moment in their cycle, and they go higher and higher with minimal effort. Push at the wrong moment, out of phase, and you're fighting them. Same thing with electrical circuits. Inductance and capacitance together create a natural oscillation frequency for any circuit. Drive, the system at that frequency, and the impedance, well, not exactly vanishes, there's always some resistance, but it minimizes, the current maximizes, the power transfer becomes enormously efficient. This is why radio tuning works. Your antenna circuit is designed to resonate at the frequency of the station you want to receive. Other frequencies pass through mostly unaffected. Only the resonant frequency drives the circuit effectively. And this is where I saw the future of power transmission. If the field carries the energy, broadcast it. Eliminate the wires entirely. Build a tower that generates a standing electromagnetic wave in the Earth ionosphere cavity. Any receiver anywhere on Earth could tap into that field and extract power. Wireless power distribution for the entire world. It didn't work. Not for economic reasons, though those mattered, but for physics reasons I didn't fully appreciate. The inverse square law. Energy spreads in three-dimensional space. The intensity drops as 1 over the distance squared. Without the wire to confine it, the field disperses. You'd need enormous power at the source to deliver useful amounts of power at any distance. Terribly inefficient unless you can somehow confine the field, which we couldn't do. But near-field coupling works fine. Those phone charging pads, key chargers, they use oscillating magnetic fields over short distances. RFID chips in your credit cards, same principle. The field stays concentrated in a small region. Efficiency is acceptable for small distances. The principle was sound. I believed I could eliminate the distance problem through resonance effects and earth grounding. I was wrong about the economics. Wires turned out to be cheaper than broadcasting power to everyone, even if we could have solved the efficiency problem. My vision was correct about field primacy, that electricity is fundamentally about field dynamics, not particle motion. I was wrong about the practical implementation at global scale. But now they're reconsidering wireless power for electric vehicles, charging while driving. Maybe 130 years later, the economics have changed enough to make it viable. Let me tell you what resistance really is, since we've been talking about how electrons barely matter. The common explanation says electrons bump into atoms in the wire, like balls bouncing off obstacles. That's not quite right. Better to think of it as electrons interacting with phonons, quantized vibrations of the atomic lattice. The field energy transfers to thermal motion. The wire heats up. This is why incandescent light bulbs work. You run current through a thin filament. Field energy gets converted to heat through these electron-phonon interactions. The atoms vibrate faster and faster until they're vibrating so violently that they radiate electromagnetic waves we can see. Light, but it's incredibly inefficient. 95% of the energy becomes heat, maybe 5% becomes visible light. Compare that to LEDs, where you have direct field-to-photon conversion. Electron drops from higher energy level to lower energy level, emits a photon directly. No thermal middleman. Much more efficient. So even in these supposedly electron flow devices, what actually matters is the field-electron interaction, not electrons traveling any distance. The electrons in your light bulb filament aren't flowing from one end to the other, carrying energy like water, carrying logs downstream. They're vibrating in place, interacting with the field, converting field energy to other forms. Resistance isn't an obstacle in the path. It's the coupling strength between electromagnetic field and matter. Some materials couple strongly, high resistance, field energy transfers readily to heat. Other materials couple weakly, low resistance, superconductors at the extreme, which raises something deeper about what electricity fundamentally is. We've been thinking backwards about reality for a long time. Particles seem real, solid, fundamental. Fields seem abstract, mathematical, derivative. We think electron is a thing, and it creates a field around itself. Actually, it's reversed. Fields are fundamental. Particles are localized excitations in those fields. An electron isn't a little ball of stuff that has an electromagnetic field around it. An electron is a stable pattern, a quantum of the electron field. A photon isn't a particle of light that sometimes acts like a wave. A photon is a quantum, a discrete excitation of the electromagnetic field. Everything is fields. Matter, light, forces, all of it is vibrations in various quantum fields. Modern physics, quantum field theory, has confirmed this. I felt this in the 1890s without the mathematics to prove it. The ether doesn't exist, not in the way we imagined it, but something fills space. That something is the field. Multiple fields, actually, overlapping, interacting. So electricity isn't electrons moving through wires. It's an electromagnetic field. Configuration change, propagating through space. The wire guides it, but doesn't carry it. The field does the carrying. AC works not because particles flow, but because the field oscillates, and that oscillation transports energy. Resistance is field matter coupling strength. Everything comes back to the field. When you flip a light switch, you're not sending electrons on a journey. You're changing the boundary conditions of an electromagnetic field that already permeates the space, and that change propagates outward at light speed, guided by the geometry of the conductors. How does the field store energy? What is energy in a field, physically? That's a different story. I've got to stop somewhere. But you see, the deeper you look, the less solid it all becomes. What seems obvious and material, particles flowing, carrying charge and energy, dissolves into something stranger. Configurations of fields, oscillations in space itself. And somehow that abstraction is more real than the particles we started with. The particles are just persistent patterns in the fields. Everything you think of as solid and real is waves in something that isn't material at all.